Welcome to our second video, and we have more good news. There's still a little bad news, but the bad news will become good news in a future video. So we're going to talk about general solutions, or kind of introduce the idea of a general solution for a system of differential equations that has complex eigenvalues. So specifically, to summarize something that we brought up in the last video with this matrix that we're going to look, this differential equation that we're going to look at a lot, is we're going to say and remind you all that if lambda is complex, specifically if it's not real, because technically the real numbers are a subset of the complex numbers. But anyway, if lambda is not real, then there's no straight line solutions. Okay, in the last video we said, okay, we had no straight line solutions. We had a spiral. I actually don't remember which way the spiral went. Okay, it was counterclockwise, right? We had counterclockwise spiral solutions going in towards the origin. And later in the second half of this section, we talked more about qualitative analysis of like, okay, how could we find this just with this? With everything we have on this page, we could actually determine this, and we will determine this ourselves. But we're starting this section by looking at analytic solutions mostly. So if we had a complex, not real, which again, all right, whatever, I'm just going to say it, not real, right? If lambda is not real, then we have no straight line solutions. So, but we do still have solutions, and we can still find them. And so here's the good news. The good news is that when we're dealing with complex numbers, algebra and arithmetic are the same. Okay? So all the algebra and arithmetic that we did in the last two sections for distinct real roots are the same for complex numbers. That's really, really good news. Okay, and much of calculus is basically the same too, if you think about it. And really, when you get into more complex analysis, which is often like a 300 level math course or something like that, when you get into more complex analysis, you're really going to see that the complex numbers are really like the XY plane. They're really like R2, right? The complex numbers and R2, which is again the XY plane, right? Ordered pairs. They're the same thing basically, but that's a topic for another time. All right, yeah, it's a topic for another time. I won't get too much on that. So why is this so cool? Why is this statement alone so important? And the answer is that in the past, we said that y of t equaling e to the lambda t times its eigenvector, we said that was a solution. Well, good news, it's still a solution. The only difference now is it's a complex valued solution, which is not entirely useful, I will be honest. Okay, we can find solutions, right? We can actually, we can find the eigenvector, and indeed we will, for one of these eigenvalues, and we'll have a solution to this differential equation. It's going to be a complex valued solution, which is again not that useful, because a lot of times when we're solving differential equations, we're solving application problems, and most application problems don't have uses for complex numbers, right? If I'm looking at a predator-prey model and I say there will be an equilibrium when there's 5 plus 2i rabbits, come on, what does that mean? Or if I'm looking at a spring and I say, oh, the velocity is 3 minus I meters per second. Come on, Jason. Let's be real. All right. So it's not a perfect solution. It's complex, which we might not want, but it's progress. More good news in the next video for this. What can we do with complex solutions that's actually valuable? That's the next video. But in the meantime, I claim that this is still a complex valued solution, and you could check that with some differentiation. Again, I is just a number. It can come out in front of a derivative. It's a constant. Complex numbers have some properties that aren't the same as real numbers, but most of the properties are going to hold the same. So you could take my word on this for now, or you could get some practice or read more about it. But this is still going to be a solution. So let's get some practice. Again, differential equations is a big subject, and I'm not going to teach, I can't teach like a whole linear algebra course at the same time. I can't teach a whole complex analysis course in the same time. Just know that there are very interesting areas of study that support what we're doing right now, but we don't necessarily have time to get into the theory of everything that we're using. This is a pretty applied course. We're going to be using their theory, but we're not necessarily going to be proving their theory. So let's go back to our old matrix, the first example that we did today, that we showed you the phase portrait of and the direction field. For that coefficient matrix, we found that our eigenvalues were -2 plus or minus 3i. Let's just look at one of them. Let's just look at -2 plus 3i. We could find the second eigenvector, and that could be a good exercise, but let's start with just this one. How do we find the eigenvector? And that seems a little scary because this is complex, but the answer is it's going to be exactly the same. Just remember some basic things about complex numbers. Thinking again how complex numbers are actually really just like having an x and a y. So what are eigenvectors? Eigenvectors are the vectors that satisfy this equation. Again, this is a very powerful thing, saying that matrix multiplication for an eigenvector is the same as a constant multiplication by the eigenvector. Super nice, because multiplying a vector by a constant, much nicer than multiplying a vector by a matrix. So we know what lambda has to be, we know what a has to be, so let's translate this. We're looking for values such that 2x minus 3y equals lambda times x and and 3x minus 2y equals lambda times y. And I told you in 3.2 that whenever we're finding eigenvectors, these equations must always be redundant. They need to be redundant, otherwise we messed up. That's still true. It's a little harder to see whether they're redundant. Let's simplify a bit, okay? So what do we have here for these equations? These equations become, right, that's going to be -2x plus 3xi. We're going to keep the real part and the imaginary part separate. All right. And then on the other one, okay, don't panic, everything's fine. On the other one, right, this becomes 3x minus 2y equals -2y plus 3iy. And again, I'm saying that these should be redundant. Notice, add a 2x to both sides, they cancel. Add a 2y to both sides, they cancel. So what does our equation become? Well, this first equation just becomes 3xi, sorry, let's add 3y to both sides, equals 0. Actually, I don't know if I like that. It's fine. And the other one, right, becomes 3x minus 3iy equals 0. And now these, oh gosh, I need to be consistent. Let's write the i's first. It's been a while since I've done much with complex numbers. Actually, no, let's write the I second. All right. We'll standardize that in a future video. But it doesn't really matter. It's multiplication. And you might say, Jason, these don't look redundant. But they are redundant. What happens if you multiply both sides of this equation by I? What do you get? You get 3xi, just like we had here, minus 3y I squared. I squared is -1. This becomes a plus 3y. So these are indeed the same equations. So for our eigenvector, we're just looking for any x and y pair such that y equals -x times I. Right? Divide everything by 3, move the x over. We can pick any combination here. So let's choose our eigenvector. X can be anything, and y just has to be negative that times I. So if x is 1, for example, y would be negative I. If x is I, for example, that's a really nice one, because if x is I, we get negative I squared, which is positive 1. So that's an even nicer eigenvector, I think. But again, there's many eigenvectors, and we shouldn't be surprised that this is complex, because our eigenvalue was also complex. Remember, there was a second eigenvalue for if this was a minus. We could find a second eigenvector, but we're not going to for now. So we have a solution. It's a complex valued solution, but just like before, we have a solution to our differential equation, and that's e to the lambda times t times our eigenvector. This is a solution. We could check our answer by taking the derivative. And again, I don't know what a complex number, well, I do, but you don't know probably what a complex number means as an exponent. How do you do that? What does that mean? I know what 2 squared is. I even know what 2 to the 3 halves is. We even have rules for negative exponents. What is the rule for complex exponents? Well, you're about to find out in the next video. Because I'm going to be honest, this is not very useful, but it is right about to become very useful. So the next video is a little bigger, and it introduces some groundbreaking, mind-blowing mathematics. That's not an exaggeration. And we're finally, the next video is about getting real valued solutions. We're finally going to say, how can we actually use these complex numbers to do something useful? So get excited, stay tuned, and I'll see you there. Or you'll see me there. I just see my computer screen. Bye-bye.